Well, good morning, ladies and gentlemen. Thank you for letting me speak in English. My Japanese is worse than your English, believe me. I'm glad to have the opportunity to come back to Japan. This is my 5th visit in less than 13 months. I'm always excited to come here because of the enthusiasm for these technologies in Japan. I really think that Japan is the leading country in adopting SDN and OpenFlow. So I'm always happy to return and see the progress. I spoke last in October, and previous to that in June. And after my October presentation, people said, "You didn't say anything new compared to what you said in June. You better say something new this time." So I have some new news, some new slides, and a roadmap for where we're going in 2013. I was also told you need to give some real examples of who is using this technology. So I have one of those here. It's a great example. It's even better because the customer is from Japan and the vendor is from Japan. Let me start out by giving you an introduction of why we are doing this. Enter? Okay. The main reasons anyone would adopt a new technology are two reasons. Either it saves you money or it makes you money. What operators of networks, whether they are enterprises, hosting companies, cloud providers, over-the-top providers, or telecom carriers, are experiencing is a tsunami of data. In the mobile world, we have now 5 billion people using mobile devices. 60% of the traffic is streaming media. And in the next 5 years, the volume of traffic is expected to increase 8 times to what it is now. Cloud computing has become an attractive solution for enterprises who want to lower their cost, reduce their risk, and make it easier to stay current with the latest technology. Hosting companies and cloud providers are blurred these days. Most hosting companies are adding cloud features to their services. They find challenges in the amount of data, in the degree to which companies who are their customers want to customize the services they need, and the costs they are incurring for real estate, electricity, and equipment are making it hard for them to make money. On-demand services, especially by telecom providers, are necessary to compete on a global stage, and most of them are suffering from an inability to make new services as rapidly as they would like because they have had to depend on their equipment suppliers to put those services in their equipment at their leisure. All of these factors are causing those who operate networks to to free themselves from the timetable and control of the vendors in what is turning into a revolution in networking. Enter. Yep. What did you do? Escape, enter? We'll get through this. So the new approach to networking we're calling software-defined networking. It's not as though software has not already played a large role in networking, but it was embedded software, written by the vendor, running in a proprietary system. What we have on the left is a typical network switch or router in which the silicon chips, the operating system, the control software, and the applications are all provided by that vendor. If you are an operator and you own this equipment, you buy it, you want to add a new service or feature, for example, some new kind of security feature or multicast. You have to wait for the vendor to implement it, how they choose, when they feel like it. And this has made for a limited amount of choice in the services that can be offered. Escape, enter. Two in a row. Maybe I should go through this very fast before it forgets. So we're taking the networking industry through the same change that we took the computer industry 30 years ago, to a restructuring into horizontal layers of merchant silicon running in distributed switches that are really great at fast packet forwarding, controlled by servers running software that anybody can write, and governed by applications that run on servers and that are also written by anybody using ordinary languages in ordinary operating systems. If you look at how this changed the computer world and how many applications exist in computing today, it's over 1 million. Networking will be doing this soon. We also observed in the formation of this movement that networking was really not a science but only a trade. It lacked fundamental abstractions. So this movement to software-defined networking allows us to finally institute some fundamental abstractions in networking that allow you to program the network by abstracting its characteristics and behavior. They fall into these three categories. Decoupling the applications from how the equipment is built so that the applications can be updated whenever the operator wishes without changing the equipment. Separating the control plane from what we call the forwarding plane. In other words, the software that governs where packets are routed when they come into a switch or a router does not run in the switch or router, but in a separate place where control understands the needs of the operator and its customers and the capabilities of the network. And in the move to virtualization that we've experienced with great success in computing and even storage, We are now using these abstractions to virtualize the network so that it can be operated and modified by people who don't have to configure individual devices through a command line interface. You will see that this saves operating expense, not just capital expense. Being able to program the network means you can get it to do what you want it to do by doing it yourself. One of the main factors that prompted the invention of OpenFlow was frustration by a graduate student and his professor that they couldn't program the network like they were used to programming everything else they played with. There were no interfaces into networking equipment that were open to programming. So they invented one, and that has become the OpenFlow interface. Now we will see that the important programming interfaces for network behavior live above OpenFlow in the greater realm of SDN. For those who operate networks as a service, such as telecom providers, they are able to introduce new services as fast as they can write software. Some of them have told me they can reduce their service introduction time from 3 years to 3 months. Now, by centralizing the intelligence or the control software into a server, you get the benefit of a global view of the network and this uniform programming interface. The initial benefit that most operators have realized is the ability to automatically configure networks and to reduce over-provisioning, giving them much greater utility in their network. You might have heard about the Google G-Scale WAN, which interconnects all their data centers worldwide. They are now running at a utilization of over 90%. Most networks are lucky to be running at 30%. We will also see that being able to program the network to behave in certain ways, you can apply fine-grained security and policy and compliance that gives you greater service to your customers, greater reassurance that the network is safe, and greater ability to prove that you are obeying the laws of your country. We call OpenFlow the instruction set for software-defined networking. It is a protocol for communicating between a controller that has a global view of the network and a whole array of switches. In the past, these switches had to determine how to forward packets by looking at the packets themselves and exchanging complex distributed protocols with their neighbors. This is an artifact of the Cold War in which the US Department of Defense built the precursor to the internet based on the theory that any part of the network could be destroyed at any time and there could be no central control. Centralized control does not mean a single point of failure. Logically centralized control takes advantage of the many, many advances in distributed computing that the computing world has enjoyed over the last 15 years. No single function you ever use when you go online lives in one single server and is subject to a single point of failure. Networking will now enjoy the same benefit. So instead of having to figure out what to do with every packet, the switch receives instructions from the controller to build a so-called forwarding information base or flow table. If a packet comes in and the header looks like X, The switch looks it up in the table, and it follows the instruction received from the controller. It might mean the instruction says if it comes in with this header on port 3, you send it out port 5. That's very simple. It might mean that it comes in on port 3 looking with a different header. It goes out on ports 4 and port 6. And there you have multicast through direct instruction. When I was at Bay Networks in the mid-1990s, we had multicast in our products. Nobody used it then, and nobody uses it now because it is impossible to configure. With OpenFlow, you can now directly program multicast, and you do not have to worry about trees or topologies or constraints on them in the network. You did a click here, huh? Okay. Whoa. How do I get it to go back one? Up. What goes down from the controller to the switch is a series of instructions to an OpenFlow client and a switch. What goes up from the switch to the controller are statistics and counters that tell the controller how the network is behaving. This can then go into a network application that reacts to changes in the network. Now let me give you an example from Japan. Nippon Express is a global logistics company. It's a huge company. They had all of their IT functions in different silos for different parts of the business, and they wanted to consolidate it for lower cost and greater flexibility in a private cloud. Look how widely distributed the locations of this company are. They are all over the world. They have multiple clients. They found that they could gain many benefits of the private cloud by virtualizing their servers and their storage, but they could not virtualize the network. So every time they wanted to move a virtual machine and it involved a network change, they had to reprogram all of the network equipment involved by hand, and it cost them, I'll show you a figure, nearly $100,000 per year to have this done. They also wanted to make their network more responsive to both business needs and equipment failures, and they have achieved this as well. They are one of the early pioneering customers of NEC, which has a series of products called Programmable Flow. This was the first company to put in the commercial marketplace both OpenFlow switches and OpenFlow controllers. They speak standard OpenFlow between them, so you don't have to buy both from the same company. But that's what Nippon Express did. They now have a virtual view of the network to go with the virtual view of their computing function. They can dedicate portions of their IT infrastructure in this cloud to each tenant, each customer, and they are able to make changes almost instantaneously. They also find that they can react and repair failures in the network in a small fraction of the time it used to take. They have a main site, they have one backup site, they are building more. They were able to put this new infrastructure in place in 10 days, and they immediately started seeing benefits. They reduced the amount of rack space dramatically, here by a factor of 3 to 1. They reduced the power consumption by a factor of 4 to 1. They reduced over-provisioning by the same factor, so they don't need to use as much bandwidth, they don't need as much switching horsepower, and they don't need as much computing horsepower. The outsourcing fee on the bottom left was for configuration changes. They eliminated these entirely. And they reduced their failure recovery time by 98%. They are so enthusiastic about this technology, they have become a leading champion around the world. Now let's talk about the movement of SDN, where it stands, and what the Open Networking Foundation is doing. We were launched publicly last year in March of 2011, and we are the champions of OpenFlow and SDN. In our first year, 2011, we took the ad hoc work from Stanford University and made it industrial strength, formed an actual organization and committees, and started to progress the work just on the OpenFlow protocol. In 2012, we have extended the OpenFlow protocol by, in fact, making it more extensible, adding new features to support IPv6, and also adding a basic configuration protocol for switches. These are the foundation. The value and benefit of SDN is much greater than just having the OpenFlow protocol, but we believe it is the important foundation that allows you to separate forwarding from control and get that benefit of a global viewpoint. We are totally focused on commercial success of SDN, so we have had 2 plug fests in which vendors of switches and controllers get together and test against each other to make sure they interoperate for the benefit of the customer. Based on our latest count last week, we think there are at least 64 product families that support OpenFlow, and they represent over 30 million ports in the field. Most of these are enabled through software download without changing any of the equipment. For as radical a technology as OpenFlow is, it is extremely easy to introduce into existing networks, one node at a time, through remote software download. Looking forward to 2013, we will continue to strengthen the foundation by adding new features to the OpenFlow protocol, but we are now extensively building on that foundation through structured work efforts on these 7 topics. Security of the OpenFlow infrastructure and security provided by the OpenFlow infrastructure. OAM stands for Operations, Administration, and Maintenance. It's the lifeblood of carriers to keep their networks operating full-time. We are going to be issuing a conformance testing specification, and we have already sanctioned our first conformance testing laboratory in the US, so vendors of equipment can go there and have their products confirmed as being conforming to OpenFlow version X.Y, whatever it might be. This gives the customers confidence. We would very much like to see a conformance testing laboratory facility in Japan. I will say a few more words on the next slide about OpenFlow for optical transport. We are working on hardware-accelerated switching so that the capabilities of hardware switches can be made evident to the controller without the manufacturers giving away their trade secrets. So we are abstracting those capabilities. And we are further studying the migration from legacy networks to OpenFlow networks to make it as easy and fast as possible for network operators to benefit from this technology. We are also studying the architecture and the so-called northbound API, and I will say a few more words about that. The initial examples of OpenFlow switching use the control to switch between ports on an Ethernet LAN. But there is no reason you cannot use OpenFlow to switch between fibers or wavelengths or wireless channels or frequencies. In fact, some of our members have been using OpenFlow using proprietary extensions to switch optical fiber channels. We now have a structured effort involving many companies to come up with a uniform way of doing that, because it is of great benefit, especially for people interconnecting data centers in different locations using high-speed, wide-area networks, especially under the constraints of low latency. Our effort in architecture and framework may finally answer the question of what is SDN and what is not SDN. What is in its scope? What are the elements? What are the interfaces? We have two particularly important efforts within this, in addition to the ones I'm mentioning here. One has to do with carrier requirements. We actually have a vice chair of a committee responsible for making sure we consider and meet the requirements of the telecom carriers. We are looking with great interest at virtualizing the layer 4 to 7 appliances, as are the carriers, so that the infrastructure supports this virtualized approach to not just layers 2 and 3, but layers 4 through 7. And then we have the so-called northbound API, or Application Programming Interface. It's shown in the dotted line here. We have the switches, virtual or hardware. We have the control plane software of which I spoke, and we have the network applications above it. What should the programming interface to this control software be? The answer is nobody knows. There are at least 20 examples of northbound APIs in the field today. You can go try any one you want. Tell me which one meets your needs and what those needs are. Some people think we should rush and standardize the northbound API. We are not doing that at this point in time. There are too many unknowns about what makes a good northbound API for what purposes. So what we are doing is cataloging the northbound API examples that are in the market to see how they differ and what they are good for. At that point, we will decide whether we need to step in to help the marketplace or not. So the Open Networking Foundation has a responsibility to lead this revolution in a way to make it commercially successful. We generate standards, we attract members, I'll show you who they are. But we measure our success by the commercial vitality of products and services. You wanted to know what has changed since I was here 2 months ago? Well, that change is in blue. We added a new member to the board of directors, our first enterprise, Goldman Sachs. Their network is critical to their business success. The others you are familiar with. We are, by the way, located in the heart of Silicon Valley in downtown Palo Alto. We're a nonprofit industrial consortium, but we run like a Silicon Valley startup company. We now have 86 member companies. The ones in blue have joined since I was here in October. There are 7 new companies. Only 1 is based in the United States. I'm disappointed to say that none are based in Japan, but we had quite a surge in Japanese members earlier this year and last year. You can scan this list and see if anyone important is missing. We have the chip companies, the system vendors, the software companies, the 5 main computer companies, IBM, HP, Dell, Oracle, and Fujitsu. Major software vendors, VMware, Citrix, Infoblox. Service companies, telecom equipment providers, telecom service companies themselves from around the world. We have a reseller, NCL Communications in Japan. We have startup companies that are 4 months old with 20 people, and they are members. This is an amazing community, and if you look at the quality of the people they are putting in our committees, you will be astonished, at least I am, with the high quality of contribution. If your company is not a member of the Open Networking Foundation, I invite you to consider joining, to becoming part of the movement to propel its success. Share your requirements with everyone else and be part of the innovation engine. In conclusion, software-defined networking brings great benefit to operators and users of networks everywhere. It will pervade networks wherever they are used. It's happening now. It is easy to get into it and to start with it. There's no question that it will be here for as long as there is computing, because networking will now be part of computing. The Open Networking Foundation is singularly focused on the success of this movement. It's an obligation that we are proud to carry. We hope you can be part of it. Thank you for your kind attention.